So, you've heard the term big data, right? It's this massive digital ocean of information that's all around us. But how in the world do we actually talk to it? How do we find that one specific thing we're looking for? Well, today we're diving into the special languages built to do just that. And that really is the big question, isn't it? It's one thing to have all this data, but it's another thing entirely to pull out the exact piece you need right when you need it. Every single time you refresh your social media feed or check your bank account, what's happening behind the scenes is a very, very specific question being asked to a gigantic database. So why is big data even a problem? Well, it's literally too big. I mean, at some point, the sheer amount of information just won't fit on one computer anymore, not even a giant one. So we have to chop it up and spread it out over a whole network of machines. This is what we call a distributed database. And while it solves the storage problem, it introduces this completely new and really tricky challenge. And that brings us to what I like to call the impossible choice. It's a conflict that sits at the very heart of any large database. This idea is so fundamental, it actually has a name, the CAP theorem. And to really get it, we need to meet the three main characters in our story. All right, first up, we have consistency. Think of this one as the absolute perfectionist. Consistency guarantees that anytime you ask for a piece of data, you either get the most recent, 100% correct version, or you get an error. It would rather tell you nothing at all than give you an answer it's not totally sure about. Okay, next on the list is availability. This one is the ultimate people pleaser. Its promise is simple. You ask a question, you get an answer. Every single time. It will never leave you hanging. But, and this is a big but, that answer might be just a little bit out of date. The key thing is you'll always get something. And our third player is partition tolerance. Now, this one's a bit different. It's not so much a choice as it is, well, just reality. It's the simple fact that in a huge network of computers, things are going to break. Connections will drop. A server might go offline. It's not a question of if it will happen. It's a question of when. So you put all that together and you get to the heart of the CAP theorem. What it basically says is, since those network failures, those partitions are guaranteed to happen, you have to make a choice. When things get flaky, you can have your perfect, correct data, that's consistency, or you can have a system that always responds. That's availability. You cannot have both at the same time. It's impossible. Let me break it down like this. A system that values consistency says, listen, if I can't check with everyone and be absolutely certain this is the newest info, I'm just going to give you an error. I refuse to lie. On the other hand, a system that values availability says, hey, here's the best I've got right this second. It's probably right, and it's way better than getting nothing, right? Let's keep things moving. And that one single decision, it basically splits the entire world of databases in two. So how does this impossible choice actually play out in the real world? Let's start with the classic, the original gangster of databases, SQL, or structured query language. And trust me, SQL has a very strong opinion on this whole consistency versus availability debate. The way to think about SQL is that it loves order. It sees the world as a giant, perfect spreadsheet. Everything is neatly organized into rows and columns. Every single piece of data has its own little box, its own specific, predefined place to live. For things like a bank ledger, this kind of structure is everything. So what do you actually do with SQL? Well, it's all about managing that neat and tidy data. You'll often hear developers talk about CRUD operations, which is just a handy acronym for the four main things you do: create new records, read existing ones, update them when they change, and of course, delete them when you don't need them anymore. So given that SQL is all about structure and being correct, you can probably guess which side it takes in our impossible choice. Yep, SQL databases choose consistency every single time. And it makes sense, right? When it comes to your bank account, you don't want probably the right balance. You need the exact balance. There's just no other option. But the modern internet, it's not always neat and tidy, is it? It's messy, it's fast-moving, it's kind of chaotic. For that world, we needed a totally new philosophy. And that's where NoSQL comes into the picture. So NoSQL basically looked at the perfect spreadsheet world of SQL and said, yeah, no thanks. Instead of those rigid tables, NoSQL databases use flexible documents. Think of a user profile on a social media site. One person might list their job, another might not. One might have 10 photos, another might have 0. NoSQL is totally cool with that. It's built for that kind of flexible, messy reality. And to deal with all that messy data at incredible speeds and massive scale, NoSQL makes the exact opposite choice in the trade-off. It goes all in on availability. I mean, when you're scrolling your feed, you'd much rather see a post from 2 seconds ago than get an error message while the system checks if it's the absolute most up-to-the-millisecond post from across the globe. Fast and good enough is way better than slow and perfect. Okay, so we've got SQL for order and NoSQL for chaos. But what if the thing you care about most isn't the data itself, but the connections between all the different pieces of data? Well, for that, you need a whole other way of thinking. Welcome to the world of Sparkle. This right here is the aha moment. Take a look. On the left, you've got the SQL view. It just sees a list, a table of characters. But on the right, that's how Sparkle sees the very same data. It's not a list, it's a map. It's a graph of relationships. It doesn't just know the name Rob Stark, it knows that Rob Stark is a member of House Stark. And the magic behind this is a system called RDF. Now, it sounds complicated, but the idea is super simple. All data is stored as a 3-part sentence called a triplet. You've got a subject, a predicate, and an object. So, Rob Stark, that's the subject. House is, that's the predicate or the relationship. And Stark, that's the object. The entire database is just a giant web of these simple facts. And Sparkle is the special language you use to ask questions of this giant web of facts. You can ask it to follow the connections, to find hidden patterns, to connect the dots. This is the tech that powers things like the info boxes on Wikipedia, but it's also the foundation for these huge, complex knowledge graphs that are driving cutting-edge AI and scientific discovery. Okay, SQL, NoSQL, Sparkle. That's a lot to take in. So the obvious question is, which one's the best? And the answer is, that's totally the wrong way to think about it. There is no best. There's only the right tool for the right job. So let's make this super simple. Here's your cheat sheet. If you need absolute, rock-solid, 100% correctness, like for financial transactions, you need SQL. If you need crazy speed and flexibility to handle mountains of ever-changing data, like a social media feed, you're going to want NoSQL. And if the most important thing is understanding the complex web of relationships in your data, like how everything in an encyclopedia links together, then Sparkle is your tool. Which brings us to one last big question to think about. We started with languages that think in simple lists. Then we got languages that think in flexible documents. And now we have a language that thinks in relationships. As our world gets more and more connected, and as AI gets smarter and needs to understand not just facts, but how those facts relate to each other, which of these ways of speaking to data do you think is going to be the most important one to know?